All right, now we're going to look at roots of complex numbers. So we just looked at powers of complex numbers. I do have to apologize if you hear a slight pounding sound. My neighbor upstairs is clearly hammering something. There was a saw going earlier too, so who knows. Anyway, roots of complex numbers. All right, before we get into the roots of complex numbers, I want you to recall how to solve these types of equations. So solve sine 4x equals 1/2, x cubed equals 27, and x squared plus 64 equals 0. So pause the video and solve each of those. Unpause when we're ready to discuss. Oh, and one more thing, sorry. For the sine of 4x equals 1/2, solve it on the interval of 0 to 2 pi. All right, so don't find the general solutions. Okay, now pause the video. Unpause when you're ready to discuss. All right, so for sine of 4x equals 1/2, first, remember, we want to just think about, okay, where does sine equal 1/2? But because of the 4x, I need to go 4 times around the circle because I'm trying to find all my solutions on the interval 0 to 2 pi. So sine equals 1/2 at pi 6 and 5 pi 6, and then I just keep finding coterminal angles of each of those. So 5 pi 6 plus 2 pi is 17 pi 6, plus 2 pi is 29 pi 6, plus 2 pi is 41 pi 6. Remember, all of these answers, all 8 answers here, equal 4x. So to find x, I just divide them all by 4. So I end up with my 8 answers of x equals pi 24, 5 pi 24, 13 pi 24, 17 pi 24, 25 pi 24, 29 pi 24, 37 pi 24, 41 pi 24. Wow, that's a lot of pi 24. Okay, moving on. X cubed equals 27. So if you just took the cube root of this and said 3, that's one of your 3 answers. Remember, because this is x cubed, I should have 3 answers. So I'm going to subtract the 27, factor this as the difference of cubes, x minus 3, x squared plus 3x plus 9, set each factor equal to 0, x minus 3 equals 0, and I get x equals 3. That was one of my answers. Remember, if I factor this correctly, the x squared plus 3x plus 9 will never factor. And I know it'll give me complex solutions. So I chose to complete the square, but you could also do the quadratic formula. Either way, you should end up with x equals negative 3 over 2 plus or minus 3 root 3 over 2i. So here are 2 of my answers. Here's the third. The last one over here, x squared plus 64 equals 0. So in this case, I did subtract the 64, and then I took the square root of both sides, and I get x equals plus or minus 8i. So because this was x squared, I get 2 solutions, and I did. Now, why are we doing this? Good question. Well, we're doing this because this is going to help us understand what we're going to be doing with roots of complex numbers here right now. So we learned about powers of complex numbers. Look at that little graphic with the roots. It's a different kind of roots. Also different than the hip hop group Roots. But still, it's the word roots. I digress. A plus bi is z equals r times cosine theta plus I sine theta. We know that. We know that if we raise this to a power, z to the n is r to the n times cosine n theta plus I sine n theta. So that's what we learned in the powers video using DeMoivre's. Now we want to learn about complex roots. So the first thing we want to understand, and we talked about this in the polynomials unit way back in first semester, but we know that there are going to be n complex roots, or let me rephrase that, there are going to be exactly n complex roots of a complex number. We talked about this in the polynomials unit with the fundamental theorem of algebra when we talked about that there will be exactly n complex roots of a polynomial of degree n. So this is very similar. So if I have z to the 1 over n, remember that's just a different way to write a root, now we can say that this is going to be r to the 1 over n times cosine of theta plus 360 times k over n plus I times sine of theta plus 360 times k over n, where what is this k, you ask? Excellent question. K is counting numbers starting at 0 and going up to n minus 1. So that's where we're going to get the different roots. I'll let that sink in for a minute. Okay, let's look at an example. All right, so we already saw from our 2 examples ago that the cube root of 27 is 3 negative 3 over 2 plus 3 root 3 over 2I. So we're going to look at doing this, finding the cube root of 27, but using DeMoivre's theorem. So first, I need to understand, okay, this is the number z equals 27 plus 0I. So I'm going to write that in trig form. If I was to graph this, since it's only a real part, I know that this would be the point here where this would be 27 comma 0 on my complex plane. So I know the angle is 0. So I can say z equals 27, because I know r will also be 0, because that is the distance from the origin, CIS of 0. All right, I'm going to use the CIS just for shorthand, because otherwise this gets a little messy. So we want to find the cube root. So I know the cube root of z is going to equal the cube root of 27. Now, when we're saying this cube root here, we're doing the principal root. And then it's going to be CIS of 0, because that was my theta, plus 360 times k over 3. So I need to actually figure out what are each of these 3 roots. And I know that there should be 3 roots because I'm doing a cube root. So now I'm going to actually split this up into its 3 different roots. So I know the cube root of 27 is going to be 3. So I get 3 CIS of 0 plus 360 times 0 over 3. So remember, this is because k starts at 0 and counts to n minus 1. N is 3, so the first one's going to be 0. Then I'm going to have 3 CIS of 0 plus 360 times 1 over 3. And then the third answer is going to be 3 CIS of 0 plus 360 times 2 over 3. So this is the pattern using DeMoivre's theorem. Now I do want to simplify each of these angles. So 360 times 0 is 0. So this one's going to end up being 3 CIS of 0. And this gives me the real number 3. Remember, that was one of my answers. Here, 360 times 1 is 360. 360 plus 0 is 360. 360 divided by 3 is 120. So here I'm going to get 3 CIS of 120 degrees. And then the last one, 360 times 2 is 720. 720 divided by 2 is 240. So here I end up with 3 CIS of 240. Now, for the sake of time, and because I didn't specify otherwise, I'm just going to leave my answers in trig form here. If I was to convert them back to standard form, 3 CIS of 120 and 3 CIS of 240 would convert into negative 3 halves plus 3 root 3 over 2I and negative 3 halves minus 3 root 3 over 2I. And then the 3 CIS of 0 was just x equals 3. So our 3 complex roots of the cube root of 27 are 3 CIS of 0, 3 CIS of 120, and 3 CIS of 240. All right, I want you to try this now. So using DeMoivre's, I want you to find the two square roots of -1 plus I root 3. So pause the video, do that, unpause when you're ready to check. My hint is don't forget you need to convert this to trig form first. You can leave your answer in trig form as well. Pause the video now and then unpause later. All right, here I ended up with root 2 CIS of pi thirds and root 2 CIS of 4 pi thirds. I chose to use radians here just to see how that works as well, and for practice. Don't forget you're going to need to use radians sometimes as well. So what did we do? Well, first thing was I identified, okay, if I go left 1 and up I root 3, I'm in quadrant 2. That's going to help me in terms of determining my angle. I found my r value, the square root of a squared plus b squared, and I got 2. That's a nice number. Tangent of theta equals negative root 3 if I divide b by a. So in quadrant 2, tangent equals negative root 3 at 2 pi thirds. So I know my original number in trig form is 2 CIS of 2 pi thirds. So now if I want to take the square root of this, the square root of z is going to be the square root of 2 CIS of 2 pi thirds plus 2 pi times 0 over 2, and the square root of 2 CIS of 2 pi thirds plus 2 pi times 1 over 2. So here k was 0 and 1 because I was finding the two square roots. 2 pi thirds plus 2 pi times 0 over 2 gives me pi thirds, and 2 pi thirds plus 2 pi times 1 over 2 gives me 4 pi thirds. 2 to the 1/2 is just root 2. All right, so DeMoivre's theorem now allows us to easily find powers and roots of complex numbers. It also helps us understand that every complex number has n distinct nth roots. So keep that in mind, that tells us that we can find the root of any complex number. And remember, real numbers are complex numbers as well. So you could use this to find the roots of any real numbers as well. This is also going to be something we're going to look at to find the square root of I. Remember, way back in first semester, we found the square root of I by using a different, more complicated technique. Here, we'll see how we can find the square root of I very easily by using DeMoivre's theorem.